This is a short review of quadratic functions. The focus here is on different ways that you can write quadratic functions, and then the different graphical things that you can see when you write the function in these different ways. So before we talk about kind of the key ideas of quadratic functions, we need to all agree on what a quadratic function actually is. So a quadratic function is basically any function that has a formula that looks like this. So in other words, it looks like ax squared plus bx plus c, where a, b, and c are real numbers. And we like to specify that a is non-zero. If a is 0, then you'd have a function that just looked like bx plus c, and that's what we would call a linear function. So quadratic function is anything that looks like this. Some people call it a degree 2 polynomial. And for the purpose of this video, we're actually only going to look at one example. We're just going to look at it in a lot of different ways. So the example we're looking at is f of x equals 2x squared minus 16x plus 14. And for reference sake, we're actually thinking here of a being equal to 2 and b being equal to negative 16 and c is equal to 14 in terms of this kind of formula up here. Down here at the bottom, you can actually see two other ways to write the very same formula. In other words, if you were to expand this expression right here, it would eventually be equal to that. And similarly, if you expanded this and combined like terms, that thing would eventually be equal to this. So these are really all just different ways to write the same formula. We're using the same formula that we had on the last page. And I'm on the left side, I'm just computing a few things using this formula. So just to make sure we all agree on what this means, if I write something like f of 3, what it means is I'm taking that formula that's written up there, and everywhere that I see an x, I put a 3 there. So it's 2 times 3 squared minus 16 times 3 plus 14. And if you multiply that out and add up the corresponding numbers, you're going to get that that's equal to negative 16. And so that's why we write f of 3 equals negative 16. This is a graph of that formula that you see right here. And I'm going to assume that some things about this graph are very clear to you. In other words, like the idea that f of 3 equals minus 16, that means that if you go over 3, you have to go down 16 in order to reach the graph. But I'm going to focus on these 3 points right here. And one of those 3 points is actually something that's really, really easy to see if you write the formula in the way we've got it right up there. So specifically, I want to focus on this point that's called the y-intercept. The other two that I had marked were called x-intercepts. And the real key idea here is that if you were to make up coordinates for this point right here, it's not exactly clear how high up that point is, but it's very clear how far to the right or left it is. In other words, the x value of that point absolutely has to be 0, and the y value is something that we don't necessarily know. But as soon as we look at this formula that's written up here, it should become pretty evident what the y value of that point is. And the reason is, it just requires us to plug in x equals 0. So we'll do that. F of 0 is equal to, well, it's 2 times 0 squared minus 16 times 0 plus 14. And those first two terms basically aren't there, and we're just left with a plus 14. So what that's actually telling us is that this point that's up here is the point x equals 0, y equals 14. And that's something you can always see pretty easily when you write a quadratic function in this sort of standard form, the ax squared plus bx plus c. This last term is always going to represent your y-intercept. But the most important thing from my point of view is that you can sort of picture on a graph that in order to find the y-intercept, you'd have to plug in x equals 0. On this page, we're going to focus on what some people like to call the factored form of that polynomial. That's this thing that I've underlined right here. And I actually think it's worth taking a moment just to think about how you might get that. So if you pretended, for instance, that you didn't know that on the right side, you didn't know what the factored form was, you might take this thing and say, well, is there anything that's common to all of those coefficients or all of those terms? And sure enough, you can factor a 2 out. So it's 2 times x squared minus 8x plus 7. And then the 2 is just going to kind of sit there, but then we're going to further factor this x squared minus 8x plus 7. So in other words, we're going to write this as 2 times, and then x squared minus 8x plus 7 is going to break into 2 separate pieces. And very commonly, when you're trying to factor something like this, you can get a pretty good feel for what's happening by saying, well, there's going to be maybe an x or a 2x or a 3x or something, and then you're going to have a plus or a minus, and then you're going to have 2 things on the end, and those 2 things on the end would need to have a product of 7, and that's because of the fact that we have a 7 right here. And in fact, the reason I didn't do like a 3x over here is because we need these 2 terms to have a product of x squared. So in fact, all we really need to do is think about, like, let's do some guessing. You know, if I did x minus 7 times x minus 1, those are 2 numbers whose product is 7. And when I expand this thing, what do I get? I get still a 2. And then what do I get with these 2 terms? I have squared, and then I have minus 7x, and then I have, that came from this product right here. And then I'm also going to have minus 1x, that comes from that product. And finally, I'm going to have a plus 7, and sure enough, that's the same as x squared minus 8x plus 7. So the real question that I'm interested in is, what does it actually tell us when we write our function that way in factored form? Just a minute ago, we saw that this point up here, this y-intercept, we found that by plugging in x equals 0, and that gave us that y was equal to 14. Well, now let's think about what's happening down at the bottom. What's happening here and here? On the one hand, there's something we absolutely don't know immediately when we look at those points, but there is something we do know. Both those points have a height of 0. So in other words, whatever the x value is, I'm not quite sure of that, the y value is very definitely going to be 0. Same thing here. I don't know what the x value is, but the y value absolutely has to be 0. And so that's kind of like saying, if you took this formula, whatever those x values are, they're going to produce an output of 0. So in other words, we get something like 0 equals 2 times x minus 7 times x minus 1. So we're just trying to figure out what value of x do we plug in that's going to make the right side equal to the left side. What value of x do we plug in that's going to make the right side equal to 0? And the answer is, it's actually not nearly as hard as you might think. Let's just do something a little bit naive and plug in, say, x equals 5. If I plug in x equals 5, I get 2 times 5 minus 7 times 5 minus 1. And on the one hand, we want to know what that is, but on the other hand, that's not quite true. We actually just want to know if it's equal to 0. And that's really easy to see. It's not 0 because this 2 is just a 2. 5 minus 7 is negative 2. 5 minus 1 is 4. And since none of those individual factors is 0, the entire product can't possibly be 0. If we were to plug in something like x equals 8, same kind of story, right? If you have 2 times 8 minus 7 times 8 minus 1, I don't know what that's going to be equal to, but it sure is not going to be 0 because none of the 3 factors involved is equal to 0. So with that in mind, you can start to see pretty quickly that the only things you can plug in that are going to make a 0 on the right side are the things that make these individual pieces 0. So specifically, if you plug in something like x equals 7, what do you get? You get 2 times 7 minus 7 times 7 minus 1. And although 7 minus 1 is 6, which happens not to be 0, 7 minus 7 is absolutely 0. And so that gives us exactly what we needed. It gives us a 0. So when x equals 7, y is equal to 0. And that's actually telling us that in this graph over here, this point right here has an x coordinate of 7. Similarly, if you plug in x equals 1, on the right side you get 2 times 1 minus 7 times 1 minus 1, and that's 2 times negative 6 times 0, and 2 times negative 6 times 0 is absolutely 0. So that's actually telling us that in this first x-intercept, or in this left x-intercept, that's x equals 1, and then of course y is equal to 0. So the factored form of a quadratic polynomial, in fact the factored form of any polynomial, is telling you precisely where the x-intercepts are. But it's really important to realize that when you look at a graph, just kind of a blank graph like this, the x-intercepts are the things whose height is 0. So in other words, you don't necessarily know what x is, but you know that y is equal to 0. So you're trying to set this whole equation equal to 0, and that tells you why you just have to, why plugging in x equals 1 makes it 0, and plugging in x equals 7 makes it 0. Next, we're going to focus on something that people often call the vertex form of a quadratic function, and that's this way of writing it. So we've basically written it as something that looks like a times, x minus h squared plus k. And this form that we've written it in tells us something really interesting about the graph. Now keep in mind that we already know a couple of things, right? We know that this y-intercept is at the point 0, 14. We've got a couple of x-intercepts. One of them is at 7, 0. The other one is at 1, 0. So what does this thing actually tell us? Well, what I'm going to do is write this formula ever so slightly differently. I'm going to write it as f of x equals negative 18 plus 2 times x minus 4 squared. And now I'm going to think about what happens when I plug various things into this function. So in other words, like, what's f of 6? Okay, well, f of 6 is equal to negative 18 plus 2 times, now I got to do 6 minus 4, well, that's 2, and then I got to square it. What happens if I plug in something like 1? What's f of 1? It's equal to negative 18 plus 2 times, now I have to do 1 minus 4 and square it. Well, 1 minus 4 is negative 3. And let's think carefully about this. It's going to be negative 18 plus, even though there's a negative 3 inside of these parentheses, we're squaring it, so it becomes a positive 9. So it's really 2 times 9. And actually, that ends up being equal to 0. We've seen this before. But the key idea is that it seems like no matter what we plug into this function, we're getting negative 18, and then we are adding 2 times something that's non-negative. So for instance, if I plugged in f of, let's go with 8 or something. So what's f of 8? It's negative 18 plus 2 times the square of 8 minus 4. If I plugged in negative 3, it'd be negative 18 plus 2 times, well, negative 3 minus 4 is negative 7, but I'm squaring that, so it would be 2 times 49. So really what I want you to notice is that no matter what we plug in, that answer is going to be negative 18 or bigger, because we're basically adding something to negative 18. And in fact, it's pretty clear how to get the smallest possible output in this function. If you plug in 4, what's f of 4? It's negative 18 plus 2 times 4 minus 4 squared. That's the only way that our answer is not going to be bigger than negative 18, because this comes out to negative 18 plus 0. So what that is telling us, and there's probably a little bit more thinking to do about this, but the point is I hope it's suggesting at the very least that the way we get the smallest output is by plugging in x equals 4. And in fact, what is that smallest output? It's negative 18. So this formula, when written in this particular form, is actually telling us that this function has a smallest output of negative 18, and that happens when x is equal to positive 4. One other way you can actually think about this formula that's on the right side up here is that it's basically taking the function y equals x squared, and you're doing a few things to it. You're taking y equals x squared, and then you're stretching it vertically by a factor of 2. And then you are shifting it to the right by 4. And then finally, you're shifting it downward by 18. So this is a parabola that's been shifted to the right by 4 and shifted down by 18 from the origin. And also it's stretched vertically by a factor of 2. But again, people often call this the vertex formula of this quadratic function. One more nice thing about this vertex form of a quadratic function is that it can actually help us to find x-intercepts. So in other words, these 2 points here, we found them before by factoring. But if you didn't happen to know how to factor this function, you can actually figure it out from this version of the formula. And here's how. You can say, well, again, this is, I don't know the value of x necessarily, but I know the value of y is going to be 0. Same thing here. I don't necessarily know the value of x, but I know the value of y is going to be 0. So we're setting 0 equal to 2 times x minus 4 squared minus 18. And of course, how do you solve that? You can stick the 18 on the left side. It becomes 18 equals 2 times x minus 4 squared. Then that becomes 18 divided by 2, which is 9 equals x minus 4 squared. And that means that x minus 4 is either equal to 3 or negative 3. And of course, if x minus 4 is equal to 3, that means x is 7. If x minus 4 is negative 3, that means x is equal to 1. And there you have it. We've found our 2 x-intercepts again. It's worth making one last comment about this vertex form of a quadratic function. The process of taking something that's written in this form and turning it into that form, that has a name, and that's called completing the square. And that's something that takes a little bit of patience to learn how to do, but it's definitely a topic that a lot of beginning algebra students eventually come to like a lot. The last thing I want to say is that if you don't see how to factor a quadratic function, and if you don't know how to complete the square, you still might be interested in finding the x-intercepts for that function. And to that end, there's one more way you can do it. There's this thing called the quadratic formula. And probably you've seen this before, but it's worth reviewing. The idea is that this function is supposed to have the form ax squared plus bx plus c. And in this case, the value of a is equal to 2, the value of b is equal to negative 16, and the value of c is equal to 14. And so all you have to do is plug those values into this formula down at the bottom of the page, negative b plus or minus the square root of b squared minus 4ac over 2a. And when you do that, what do you get? You get this fairly complicated looking expression, but then if you actually evaluate all those numbers in there, you get 16 plus or minus the square root of 144 divided by 4. And of course that becomes 16 plus or minus 12 divided by 4. So you're either looking at 16 plus 12, which is 28 over 4, or you're looking at 16 minus 12, which is 4 over 4. And of course, 28 over 4 is equal to 7. 4 over 4 is equal to 1. And of course, those are the two x-intercepts that we've found several other times, right? So you've got the point 1, 0, and you've got the point 7, 0. And we found those from this quadratic formula. A pretty good question to ask is, where does this quadratic formula come from? In fact, probably one easy way to answer that, takes a little bit work algebraically to see it, but the basic idea is that you can take a generic looking function, ax squared plus bx plus c, and you can complete the square. And that takes a little while to get to the point where you can do that abstractly, but once you do that, it can be used to tell you that these are your x-intercepts.